Welcome to this video. So what we're looking at here is, yesterday I seen a video from Laura of Bollywally Woo Woo on Telegram. I've seen this on X as well. It shows, or is purporting to show, the electromagnetic radiation from this smartwatch being measured on a TriField TF2. So we'll just watch this video and then we're going to discuss exactly what's going on here and why it isn't picking up electromagnetic waves from this particular watch. I'm going to do a little experiment to prove that as well. Okay then. Right, so you can clearly see there that the TF2 goes mental when this watch is put near it. Now, there's a problem here, because this is why people with these meters, which are just a couple of op amps, this is the problem with these meters, is people are using them so wrong. Okay, so what we're gonna do now, we're just gonna prove that the source of this emittance is not RF energy. Right, hello then. So we have here is our TriField TF2, and we have an LCD screen. So what I'm going to do is going to power the LCD screen on. I'm just going to make sure I'm not touching between the two contacts there, not shorting it and bridging it. Right, I'm going to fire that up on the power supply. Cool, okay. So we're going to get our TF2 meter, offer it up. Right, power that off for now. Okay, so you're probably asking, what the hell is going on here? Well, inside this is just a couple of op amps. Now, what the op amps do is they draw in an electrical signal or a current in AC, i.e. radio waves, through an antenna. There'll be a capacitive, relatively simple tuning element and a low noise amplifier as well, which will just be a transistor, a few diodes, etc. inside. It's a very simple thing, so it comes in through the two op amps. There's a little MCU in there, a little controller chip. That controller chip will take the voltage in, or at least the output voltage from those two op amps, and what it will do, it'll convert that voltage via a logarithm into a set value, and then that value is presented to you on the screen. Now, the problem with op amps is they draw in everything. I mean, everything. As you can see, that is not RF, but this is telling you it's RF. So there's clearly an issue using these. So what I'm going to do now, I'm going to use my homebrew RF meter, which I made myself, which is basically actually just doing the same thing as a TF2. So what we talked about before with the two op amps giving a voltage, obviously there'll be a voltage divider in there as well, because it won't take like a full current from the op amps. But so the op amps are exactly the same thing. They take a current, they turn it into a DC voltage, and that chip reads in. Now, well, what this does, this takes a current, it turns it into a DC voltage. On the output of that voltage, I then take that voltage reading. I have a logarithm wrote, it's not actually wrote in there, but I basically take the voltage reading and I convert it into a sensible number, which the programmer wrote to read this, then takes the logarithm. I've also got an amplifier as well, so I amplify the electrical noise that comes in. You'll notice that a lot of EMF readers do that, and usually they're very, very expensive ones. I mean, I literally built this for £40. That's all in, all the components you see there. Obviously I have these components in bulk, but if you look at that, it's about £40 all in. Yeah, so this actually goes to 10 gigahertz, 0 through 10 gigahertz, which is way more than this does at a fraction of the cost. Cool. Right, so what I'm going to do, we've already tested this meter, obviously, already tested the screen with the TriField 2. We know that this is basically giving electrical interference with this picking up on, because LCDs, LEDs, they all interfere. In fact, I can probably do that. I've got you'll hear it on the mic, but you won't see, but just the light, you'll see the light blank out, but I've got an LED light that's illuminating this workspace in a minute, so. Yeah, so it's ridiculously sensitive. Absolutely ridiculously sensitive, isn't it? Right then, so what we're going to do, we're going to fire up my meter, which doesn't use op amps. Get rid of that. Cool, and fire up the meter. So if you listen to that sound, what that sound is obviously the DC electrical current being converted. You notice a lot of the higher end meters, which don't use op amps, use this kind of analog devices chipsets. You'll notice that's the sound they make. They're literally just taking that, and then you hear that, and it's whatever they do with the logarithm, basically, how they convert that voltage into the reading we're about to see on the screen. So what I'm going to do then, I'm going to connect my software rotes when I built this, and we're just going to see a load of RF emissions going on once it settles in, so you can already see the RF emissions there. Varying intensities. Right, cool. So what we're going to do now, we're going to get our LCD screen. Yep, right up against the antenna. This antenna has got way more gain than the one in the TriField. And you can see it's nothing. So what's happening is, I'll just disconnect that and kill you, because that noise can be quite annoying. Right. In fact, I'll just unplug that so I'm not pulling it off the desk. I'll just drop the lead off the desk instead. Okay, so this is why these EMF meters that use op amps are basically rubbish. Absolutely rubbish. In fact, we'll go again with that. So you can see how my £40 meter performs a lot better at distinguishing between interference than this that's just full. Well, got a couple of op amps in it, and the problem with the op amps is as well because I've got antenna diversity here, so I can change this antenna out for say a 2.4 gigahertz antenna, but this is a logarithmic wideband antenna. This goes from I think 300 megahertz through to like 6 gigahertz. Don't quote me on that. I could be wrong. It could be higher. It could be lower. I can't quite remember. But it does what I need it to do in the ranges I need it to do it. Although for a specific, say I was out looking for 5G, 3.6 gigahertz, 3.5 gigahertz in the UK at this moment in time, I would have a tuned 3.6 gigahertz antenna. If I was out for 4G, the same thing. I'd have an 1800 megahertz or 2.2 gigahertz antenna tuned for that frequency. Then that way I could deduce the decibel gain of that antenna, and I would know approximately, doing a reverse power density equation, what that tower was putting out. So I could factor down the gain of the antenna, or the gain of the low noise amplifier I've got on the antenna if necessary. And I could also factor out this coaxial cable's decibel loss and come up with a reasonably there or thereabouts. I mean, this isn't a £10,000 spectrum analyzer, is it? But a reasonably there or thereabouts what that signal emission is. And by using obviously a logarithmic directional wideband antenna, you can, or any directional antenna for that matter within those bands, you could pinpoint that tower and know that you have a line of sight approximately, if you were 40 meters away, then you would know that anything within 10 meters, you're here, it's going to travel outwards, and you know that anything within a 10-meter area around that tower is your emission. So if you've got a couple of towers next to each other, you may have to try and factor out who's the who, basically who's who in the emission. But generally, you would then, if you were doing that, you wouldn't do that with this. You would do that with a spectrum analyzer. Obviously, this is just built this just for the sake of showing how shit these are, really, and for other debunking stuff as well. And this is accurate as well. It's got a noise floor of 65 decibel. It won't go below that noise floor, which is neither here or there, because most of the signals you're looking for, right, are going to be above minus 65 dB, but it'll only go to minus 65 dB on the noise floor. But it will go up to, I think, plus 10 dB, something like that. So that's great, and it's from zero, which is cool, all the way through to 10 gig. I mean, that's 10 gigahertz. That's amazing. That is really amazing. I've got actually a couple of these. This one goes to get up to camera actually if I can. This one goes to 8 gig. That one's the 10 gig version. Now the beauty of these is that analog devices chip there that's doing the work. They do a 10 through 26 gigahertz version of that, and the pinout is exactly the same. So I could get my reflow gun, chip that off, clean it up, drop some some flux in there, and just buy that chip, probably 50p or whatever for the 10 through 26 gig, drop it in there, and as long as that voltage regulator meets the demand of that chip, happy days. So that's a really good thing to have, and I might do that in the future, and then drop a 10 through 26, and then mount that, get a bigger board, rebuild this, and then mount it so I've got an option to select between 10 through 26 gigahertz and 0 through 10 gigahertz, which would be really bloody cool. And okay, I can technically using the logarithm on the back end, although it's going to be really finical and quite difficult to do. I can, with the logarithm, separate out individual frequencies within a set. I don't know how many. If we're talking hundreds of megahertz, you couldn't zone in on, say, somebody was keying up the mic on a CB radio and 27 megahertz. You couldn't zone in on that particular channel per se. But you could zone in on an emission, whether it be in 4G, 5G, or Wi-Fi, ISM band, 868 megahertz type thing. Potentially you can do that. So yeah, they're really cool. So that's why I built that. In fact, this isn't a video to say how I built it. Obviously, if you watch the other video, I do a build montage of that, but that's basically what this is. I built this, excuse me, I cannot say that word to save my life. Specifically, there you go, nailed it. Specifically, built this to debunk these pieces of wank. I mean, these are terrible. They're just a few. I mean, I say they're terrible, and I say that in a duality of term, basically. So these are great for finding emissions that there is no other emissions near. They're great at finding magnetic and electrical stuff, and I wouldn't trust it, but I suppose you could maybe find wires in your wall before you drill holes and stuff like that with the magnetic and electrical settings. But for RF, having 2 op amps, just sucking in all that current, so it's a current to voltage conversion. Yeah, no. As Dave says to me, E-blog, yeah, nah. Here comes a gutser. Yeah, EV blog, of course. But yeah, so yeah, it's terrible. It's absolutely terrible. But yeah. Yeah, and that is what is happening on that video. I think pretty much done here, so I'll wrap it up. But yeah, before I wrap it up, I will just say, when you see videos of people like this running round going, oh, it's 5G, it's probably bloody the news or radio broadcast, a local radio station or something like that. And it's all of the above, basically. This is just sucking in. And that antenna in there is just tuned to a specific frequency, smack bang in the middle. You don't know what's coming into this. You can't tell. If you took this out and a spectrum analyzer, you'd chuck that in the bin. You would be like, wow, I'm stood in front of this 3.6 gigahertz, MIMO pico cell, and this is telling me that this 5G is kicking out X amount of milliwatts per square meter, whereas the spectrum analyzer is telling you that per square centimeter it's putting out a magnitude less power, because you're literally picking up a TV station, or well, not just station, but you're picking up TV, radio, point-to-point comms, police and emergency services communications, the guy down the road with his ham radio, the ham radio repeater is him and his friends use in town, Tetra, DMR, the works. It's picking up every single bit of that. So yeah, next time you see people going, oh, look at this, man, look how dangerous that is, well, that's, switch it off so don't cross-go. That is just a TFT screen with nothing plugged into it. There's no chip in there, no nothing. That's all it is. So I'm going to conclude there, and thanks for watching the video, and I'll catch you in the next one, and stay safe. Don't believe idiots who are telling you what these are telling them, because they don't know what this is telling them, and they're using it wrong, okay? They're using it wrong. See somebody make something like that, then yeah, if you see somebody, actually, can I get that in shot? See somebody with a spectrum analyzer plugged into a computer, and they've used a VNA to calibrate this, and to calibrate that coax, so they know what the loss tangent is, and what the factors are involved, and they've done the math for line loss, then yeah, trust that guy. Don't trust that guy. Alright, catch you in the next one.